Researchers in the United Kingdom have revealed what they believe may be the most compelling evidence yet for life beyond our solar system. Scientists are now 99.7% confident that they have detected chemical signatures on a nearby exoplanet that could only be explained by biological processes. This potential breakthrough could drastically reshape our understanding of life in the universe. For the first time, Earth may no longer be viewed as the sole cradle of life. The search for extraterrestrial existence has become far more tangible, and the evidence may be much closer than once imagined. Humanity's curiosity about life beyond Earth is hardly new. For centuries, tales of mysterious lights, flying saucers, and alien encounters have dominated both folklore and fiction. But our current search is no longer fueled by speculation or myth. Instead, advanced telescopes, satellites, and scientific frameworks now drive our investigations. Where once people focused on sensational stories, researchers today are turning to data, looking deep into the cosmos for signs of habitability and biosignatures. Government agencies have slowly begun to release documents about unidentified aerial phenomena. Yet solid proof of alien life has remained elusive. Rather than chase the skies for unexplained crafts, scientists have redirected their efforts to the stars themselves, specifically to planets orbiting faraway suns, known as exoplanets. The expansion of this search has been greatly empowered by space telescopes capable of examining distant atmospheres. By observing how a planet dims the light of its host star during transit, scientists can analyze what gases exist in its atmosphere, searching for those linked to living systems. Exoplanets come in many forms. Some are massive gas giants with thick, uninhabitable atmospheres, while others are scorched deserts or frozen worlds. But the most intriguing ones are those located within the so-called habitable zone of their stars, the orbital region where liquid water could potentially exist. Since water is foundational to life on Earth, its possible presence on other planets makes those worlds prime candidates for further investigation. Among the many exoplanets under study, K2-18b has emerged as a particularly fascinating target. Although initially identified by earlier telescopes, new data from the James Webb Space Telescope, JWST, has revealed far more intricate details. Positioned within the habitable zone of its host star, K2-18b shows signs of complex chemicals, including methane and carbon dioxide. These molecules, while not definitive signs of life, are involved in processes that support life on Earth. What captured even more attention was the possible detection of dimethyl sulfide, DMS, a gas predominantly produced on Earth by marine microorganisms such as phytoplankton. DMS is not yet confirmed to exist on K2-18b, and the signal requires further validation. Yet its presence, even as a tentative indicator, is enough to stir considerable scientific excitement. The JWST's ability to filter starlight through the exoplanet's atmosphere has opened the door to identifying such subtle chemical clues. Because direct imaging of exoplanets is still extremely limited, researchers rely on techniques like spectroscopy, studying how molecules absorb or alter starlight passing through an atmosphere. K2-18b orbits a red dwarf star, a type of star that is smaller, cooler, and more common than our Sun. These stars can be volatile, emitting flares that may affect the atmospheres of nearby planets. The stability of K2-18b's host star remains uncertain, and this variable could play a major role in the planet's potential to support life. However, with JWST's high sensitivity, scientists are moving beyond mere detection. They're starting to analyze atmospheric temperatures, cloud compositions, and chemical distributions, enabling a richer portrait of distant worlds. One emerging theory about K2-18b is that it may be a Hycean planet, a type of exoplanet thought to have a thick hydrogen atmosphere overlaying a deep liquid ocean. If such an ocean exists and supports microbial life, then some of its chemical byproducts, like DMS, could rise into the atmosphere. Detecting those signals, especially across trillions of miles, is a significant technical achievement, but it's also what gives K2-18b such compelling potential as a candidate for alien life. There's reason to be cautious, though. DMS can potentially form through unknown chemical or geological processes that don't involve biology. Scientists are keen to stress this point. they do not yet claim definitive proof of life. Other scenarios, such as sensor anomalies or atmospheric reactions unrelated to biology, must first be ruled out. The research teams remain transparent about these uncertainties. An ongoing analysis will determine whether the signals hold up under more scrutiny. In addition to DMS, the presence of methane and carbon dioxide tells scientists about the possible chemical cycles at work on K2-18b. On Earth, these gases can originate from either biological or geological activity. Their simultaneous detection on an exoplanet invites further inquiry into how they might interact and whether the planet's environment is conducive to life. Spectroscopy, the technique used to analyze these gases, works by separating incoming light into its spectrum and identifying absorption patterns unique to each molecule. The James Webb Space Telescope, stationed beyond Earth's atmosphere, avoids interference from our planet's own gases, making it ideal for this kind of sensitive work. However, telescope time is highly competitive, and securing a slot for a planet like K2-18b means its initial data must have shown considerable promise. That early promise has certainly delivered. Some researchers now speculate that K2-18b could be a full-fledged water world, possibly home to vast, deep oceans beneath a dense hydrogen envelope. Water worlds, if they exist in large numbers, could significantly expand the zones where life might arise. Here on Earth, organisms thrive in places where sunlight barely penetrates, such as the ocean floor near hydrothermal vents. If similar conditions are present on K2-18b, then even in the absence of sunlight, chemically driven ecosystems might be possible. Yet, caution persists. The ocean on K2-18b may not even be water in the traditional sense. It could be a different liquid, such as ammonia or methane, under high pressure and low temperatures. The planet's estimated temperature, around -48 degrees Celsius -54 degrees Fahrenheit, raises questions about what kind of liquid might exist and under what conditions. With a gravity estimated to be several times stronger than Earth's, any native life would likely evolve under very different physical constraints. And even if the planet supports an ocean, the atmosphere appears hostile to humans. Thick with methane, carbon dioxide, and likely unbreathable. That doesn't rule out microbial life, though. In fact, it makes microbial ecosystems a more plausible early target for discovery. K2-18b's scale adds more intrigue. With a diameter 2.6 times that of Earth and a mass nearly 9 times greater, the planet fits somewhere between a super-Earth and a mini-Neptune. That categorization influences how scientists model its atmospheric layers, pressure systems, and interior structure. Whether it has a rocky surface beneath all those layers remains unclear. Despite all the excitement, one major barrier looms: distance. K2-18b is located a staggering 124 light-years away, over 700 trillion miles. With today's spacecraft, reaching it would take more than 1,000,000 years. Even our fastest robotic probes would struggle to get to the nearest star system, let alone 130 times farther. This makes direct exploration impossible for the foreseeable future. Instead, astronomers must rely on instruments like JWST to gather information remotely during periodic planetary transits. Even though K2-18b remains well out of reach for human or robotic missions, astronomers aren't discouraged. On the contrary, the inability to travel there makes remote observation all the more crucial. Each time the planet crosses in front of its star, scientists gain another opportunity to study its atmosphere using the transit method. Repeated passes offer improved accuracy, allowing experts to detect subtle patterns in light absorption that might reveal more about the planet's chemistry, cloud cover, and potential oceans. Not all experts agree on how to categorize K2-18b. Some argue it is a water world, rich in liquid beneath a heavy atmosphere. Others believe it's more accurately described as a mini-Neptune, an icy planet with thick gaseous layers and limited potential for hosting life as we understand it. This debate, while technical, carries major implications. A mini-Neptune suggests a harsher, more volatile environment, while a water world implies a greater chance for biologically friendly conditions. These differing views often arise from how scientists interpret incomplete data. Measurements of the planet's size, mass, and atmospheric makeup can lead to multiple models, each pointing in a different direction. For instance, if the hydrogen envelope is too thick, it could prevent stable bodies of water from forming. But if the right balance exists between atmospheric pressure and temperature, vast oceans might still lie hidden beneath the clouds. In addition to classification challenges, scientists are carefully examining whether the DMS signal, potentially a biosignature, could have a non-biological origin. While DMS on Earth is tied to marine plankton, it's essential to recognize that other planets could harbor unknown chemical processes capable of producing similar gases. Since Earth is the only known planet with life, researchers must approach any new discovery with caution. Extraordinary claims, as always, require extraordinary evidence. From the beginning, the teams involved in the K2-18b studies have been transparent about the tentative nature of their findings. Some even caution that the DMS signal might disappear with more advanced data processing. Instruments can produce false positives, especially when dealing with the faintest signals across light-years of space. That's why upcoming rounds of data collection and peer review will be essential. If the DMS detection remains consistent, the next step is to investigate whether it could arise through geochemical pathways. If none are found, then the biological explanation gains credibility. The chemical profile of K2-18b's atmosphere, methane, carbon dioxide, and potentially DMS, offers a window into its inner workings. On Earth, methane has both biological and geological sources. When found alongside other specific gases, it helps paint a broader picture. If this mixture appears tuned to support or result from life, the case for habitability strengthens. Scientists use a technique called spectroscopy to identify these gases, breaking down incoming light to see which wavelengths are absorbed or altered by atmospheric molecules. Each gas leaves a unique fingerprint on the spectrum. Methane, for instance, absorbs light at certain bands, as does carbon dioxide. The same applies to DMS and other potential indicators. Thanks to the JWST's instruments, which operate beyond Earth's atmospheric interference, scientists can read these signatures with greater precision. This orbital vantage point has redefined our ability to assess distant planets, but it comes with trade-offs. Telescope time is limited, and the demand from researchers worldwide is intense. K2-18b earned its spot under JWST's lens because preliminary findings were compelling enough to justify deeper investigation. As results emerged, a new hypothesis gained momentum, that K2-18b might be a water world, a type of planet wrapped in a hydrogen-rich atmosphere with a global ocean below. If true, the possibilities are vast. In theory, such worlds could host alien plankton-like organisms or other aquatic life forms adapted to exotic conditions. Earth's oceans have taught us that life can thrive even in complete darkness and extreme pressure, such as at the bottom of our deepest trenches near hydrothermal vents. If similar energy sources exist on K2-18b, such as underwater vents powered by internal heat, they could offer stable environments for microbial ecosystems. But water alone doesn't guarantee life. The ocean on K2-18b might not even be water in the familiar sense. Some models suggest that ammonia, methane, or other compounds could serve as liquids under high pressure and low temperatures. In fact, Saturn's moon Titan has methane lakes, demonstrating that liquid doesn't always mean H2O. Temperature estimates for K2-18b complicate matters further. The planet may hover around -48 degrees Celsius, which would normally freeze water. However, high atmospheric pressure could keep certain liquids in a stable state. That said, any human visitors, if such a thing were ever possible, would find the environment extremely hostile. Its atmosphere, rich in methane and carbon dioxide, would be toxic to us. But for researchers, habitability doesn't require human comfort. It only requires conditions where life could exist in some form. Comparisons are often made between K2-18b and some of the icy moons in our own solar system, such as Europa, orbiting Jupiter, and Enceladus, orbiting Saturn. Both moons have ice-covered oceans and may harbor subsurface ecosystems. Though they lack thick hydrogen atmospheres, the concept is similar: life protected beneath layers of shielding, possibly in warm pockets near hydrothermal activity. In K2-18b's case, if alien life exists, it might reside not on a rocky surface but deep within its ocean layers. Some scientists imagine depth-based ecosystems, teeming with microbial life or perhaps larger aquatic creatures adapted to crushing pressure and darkness. Still, there's always the chance that K2-18b is more like an icy mini-Neptune, a planet so dense and gaseous that life, at least as we know it, might be out of the question. K2-18b is about 2.6 times wider than Earth and nearly 9 times more massive. That kind of scale brings extreme gravitational differences, which would impact any living creature's biology. If life exists there, it would likely look nothing like life here. These unknowns leave the planet's classification straddling categories. Too big and dense to be a typical Earth twin, yet too complex and layered to be written off entirely as a gas giant. Distance, however, remains the largest barrier. K2-18b is about 124 light-years away, or roughly 700 trillion miles. With current spaceflight technology, it would take over 1 million years to get there. Even our fastest robotic probes would need tens of thousands of years just to reach the closest star system, Proxima Centauri, which itself is 30 times closer than K2-18b. This makes any physical mission to the planet unthinkable with today's engineering capabilities. Despite this, astronomers aren't slowing down. They continue using remote sensing methods and instruments like the JWST to gather indirect but increasingly powerful clues. Long-distance exploration is now an exercise in persistence and precision. Every planetary transit, every chemical signature, every new observation helps refine our picture of what K2-18b might truly be. For those who find the 124 light-year journey to K2-18b daunting, even in theory, astronomers have identified other exoplanets that are closer to home. While still far beyond our physical reach, these candidates offer more realistic targets for future observation or, in the very distant future, potential unmanned missions. Two of the most prominent examples are Proxima Centauri b and Ross 128b. Proxima Centauri b lies just 4.2 light-years away. That proximity makes it part of the Alpha Centauri system, the closest stellar neighborhood to Earth. Despite being much nearer than K2-18b, the challenges of reaching it remain immense. At today's fastest speeds, any probe sent would still take tens of thousands of years to arrive. Nonetheless, that distance is a fraction compared to the journey to more remote targets, which places Proxima Centauri b high on the list of observational priorities. The planet orbits a red dwarf star, like K2-18b's host. Red dwarfs are smaller and cooler than our Sun, which means their habitable zones are also tighter and closer to the star. That creates a double-edged scenario. While the planet may lie in a temperature range that permits liquid water, it also faces the intense challenge of being exposed to frequent stellar flares and radiation bursts. These flares could strip away any atmosphere, making the surface uninhabitable. Alternatively, if the planet has a strong magnetic field or a dense enough atmosphere, it might shield itself from these dangers. Researchers are still working to determine whether Proxima Centauri b has such protective features. Ross 128b offers another intriguing possibility. Located about 11 light-years from Earth, it is also tied to a red dwarf but one that appears to be less active than Proxima Centauri. That relative calmness reduces the likelihood of harmful flares, making it a more stable candidate for potential habitability. Ross 128b orbits much closer to its star than Earth does to the Sun, but because of the star's low output, the planet may still enjoy Earth-like temperatures. Estimates suggest that average surface conditions could hover around 23 degrees Celsius 73 degrees Fahrenheit, a near-perfect scenario for life as we know it. However, like other distant planets, Ross 128b still poses many unknowns. Scientists do not yet know whether it has an atmosphere, let alone what it might contain. A magnetic field, which could shield its surface from solar radiation, has also not been confirmed. The presence of water, clouds, or biological markers remains theoretical until more refined instruments can provide clearer data. Both Proxima Centauri b and Ross 128b remain at the forefront of observational campaigns. Techniques like the transit method and direct imaging, though difficult, continue to evolve. As telescopes improve, researchers hope to isolate atmospheric compositions and search for the kinds of gas combinations that hint at life. Oxygen, methane, carbon dioxide, or less familiar compounds. These nearby worlds may eventually yield data that is easier to interpret than that of K2-18b due to their relative proximity. K2-18b, of course, retains a unique place in this exploration, not because it's close, but because of the chemical signals it emits. Its apparent atmospheric blend makes it a standout in the current list of over 5,000 confirmed exoplanets. But if future telescopes spot stronger biosignatures like DMS or similar gases on planets just a few light-years away, that would be even more compelling. A nearby candidate showing signs of life would not only spark global scientific excitement, but it might also force real discussions about how to send probes, even if generational or artificially intelligent missions are required. Beyond any single planet, the broader search for life in the universe is expanding at an unprecedented pace. Some astronomers believe that if K2-18b holds even a slight promise, then the probability of life existing somewhere else in the galaxy is significantly higher. Red dwarf stars like the one K2-18b orbits are extremely common, making up nearly 75% of the stars in the Milky Way. If even a small fraction of them host habitable planets, the numbers suggest that life-bearing worlds could number in the billions. Yet it's important to remember, being in the so-called habitable zone only means that the conditions might allow for liquid water. It does not confirm the existence of life or even the ingredients needed for it. That's why astronomers are extending their search to other places too, including within our own solar system. Some of the strongest potential for alien ecosystems lies not on exoplanets, but beneath the icy crusts of moons like Jupiter's Europa or Saturn's Enceladus. Missions like NASA's upcoming Europa Clipper will specifically investigate these environments, searching for chemical signs in subsurface oceans and the plumes that occasionally burst through the surface ice. Enceladus, with its geyser-like jets, has already provided hints of hydrothermal activity, an energy source that supports life in Earth's deepest ocean trenches. If these icy moons show that life can exist without sunlight, relying instead on chemistry and internal heat, it broadens our entire concept of habitability. Even without the ability to visit distant planets, Earth-based and space-based observatories are getting better at analyzing faint signatures of life. Older instruments were more geared toward spotting massive gas giants. Today's sensors, like those on JWST, can detect much smaller, rocky planets. They can even begin to assess cloud formations, possible oceans, and how light bounces off planetary surfaces. That kind of detail, especially across such vast distances, would have seemed impossible just a generation ago. K2-18b's profile has helped introduce an entire category of possible ocean worlds wrapped in hydrogen envelopes. These worlds, sometimes called Hycean planets, may not all be the same. Some could have shallow surface oceans. Others might be layered with deep, pressurized seas stretching far beneath thick gaseous atmospheres. Life there, if it exists, might be nothing like the forms we know, relying on unfamiliar metabolic processes or energy cycles. Scientists are also exploring how life might shape a planet's atmosphere over time. On Earth, living organisms altered the chemical makeup of our atmosphere, eventually filling it with oxygen. By comparing exoplanetary atmospheric compositions with Earth's history, researchers hope to identify potential analogs. Even if the molecules involved are different, the pattern of change itself, unnatural imbalances in gas ratios, for instance, could serve as a telltale sign of biology at work. And while K2-18b isn't being touted as the definitive location of extraterrestrial life, its case is one of the most compelling so far. It represents the intersection of possibility, technology, and evidence, a rare combination in the still young field of exoplanet biology. Scientists acknowledge that future observations might rule out DMS, or offer alternative explanations for the chemical readings. Still, the research doesn't end there. Each atmospheric transit of the planet provides new data, new challenges, and new ways to understand what may be unfolding so many trillions of miles away. The growing catalog of over 5,000 confirmed exoplanets represents far more than a statistical milestone. Each discovery adds a piece to the broader puzzle of our universe's diversity. While early efforts in exoplanet detection were largely limited to identifying massive gas giants, Jupiter-like behemoths orbiting close to their stars, Modern tools and techniques now allow astronomers to detect smaller, rocky, and even temperate planets. Many of these new finds lie in habitable zones, where the balance of stellar radiation and planetary conditions could, in theory, support life. What was once speculative has become methodical. Instruments like the James Webb Space Telescope, JWST, the European Southern Observatory's Extremely Large Telescope, ELT, and the upcoming Nancy Grace Roman Space Telescope will sharpen our gaze into far-off planetary atmospheres. They'll not only confirm the presence of certain gases but might also detect seasonal shifts, atmospheric layering, cloud dynamics, or the flickers of auroras, each of which adds depth to our understanding. This technological leap also brings a shift in scientific culture. The search for alien life has moved from the fringes of speculation into the core of empirical investigation. Serious institutions now allocate substantial resources to the study of astrobiology and planetary atmospheres. Universities train students not just in astrophysics, but in exoplanet climatology, comparative planetology, and astrochemistry. What was once the realm of science fiction is now a rigorous scientific discipline. This change also reframes the question we ask. Instead of "Are we alone?" the question becomes, "How common is life?" That subtle difference carries enormous philosophical weight. If life is detected on even one other planet or moon, the odds shift dramatically. The discovery of a single microbe or chemical signal too strange to occur without life would imply that the universe could be brimming with it, spread across vast distances, emerging under varied conditions. K2-18b has become a symbol of this shift. It's not necessarily the most Earth-like planet, nor is it the closest, but the nature of its atmosphere and its position in the habitable zone have made it a test case for just how much we can learn using current tools. If future observations confirm that some of the gases seen there, especially dimethyl sulfide, truly originate from lifelike processes, that will challenge nearly every model we've held about life's uniqueness and rarity. Even if those signals are disproven, the methods used to analyze K2-18b will be refined, expanded, and applied to other candidates. Dozens of similar planets await deeper investigation. Some may be closer. Some may orbit more stable stars. Others may exhibit more extreme or more favorable conditions. The key takeaway is that we now possess the tools to study these worlds seriously, and we're only getting started. Looking ahead, astronomers are already dreaming of the next generation of telescopes and missions. Some projects aim to directly image exoplanets, not just infer their presence from transit dimming or spectroscopic signatures, but actually capture visible or infrared light reflecting off their surfaces or cloud tops. That kind of data would allow scientists to model landscapes, estimate weather systems, and perhaps even witness atmospheric patterns that are unmistakably dynamic or biological. Long-term proposals even consider space telescopes that work in tandem, spread across distances to form virtual arrays. These observatories could achieve resolutions fine enough to detect artificial lighting on a planet's dark side, or track the spread of plant-like organisms across continents, assuming such things exist and emit recognizable signals. What's become clear is that we stand at the beginning of a new chapter in cosmic discovery. It's a chapter no longer limited by speculative philosophy or constrained by incomplete technology. Today's astronomers are armed with instruments that reach across the stars, decode chemical whispers from alien skies, and, perhaps most thrillingly, move closer to answering one of the oldest questions humanity has ever asked. If solid evidence of life were to emerge from a planet like K2-18b, it would mark one of the most significant turning points in human history. The implications would ripple far beyond the realm of astronomy, touching philosophy, religion, politics, education, and global cooperation. For the first time, we would have proof that life is not a singular event confined to Earth but a possibility that emerges under the right cosmic conditions. From a scientific standpoint, it would open up an entirely new field of comparative biology. Researchers would study alien biochemistry to determine whether it resembles life on Earth or follows entirely different rules. Are carbon and water still the backbone? Or would we encounter new molecular frameworks, perhaps silicon-based life, or ecosystems sustained by energy sources never before considered viable? The discovery would also reshape the priorities of space exploration. Budgets might shift from purely technological development toward targeted life detection missions. Agencies would prioritize telescopes, probes, or even theoretical propulsion systems that could one day reach exoplanets. A new era of interstellar biology could emerge, where our understanding of life becomes a universal, not just terrestrial pursuit. On a philosophical level, the implications are even more profound. For centuries, humanity has often placed itself at the center of existence, interpreting our uniqueness as evidence of cosmic isolation or special creation. But if microbial life or something more advanced exists elsewhere, that narrative changes. We become one thread in a much larger fabric. That realization could foster a humbler, more interconnected worldview, highlighting the shared nature of life rather than our divisions. Religious and cultural interpretations would undoubtedly evolve. Some belief systems might integrate the discovery as evidence of divine creativity across the universe, while others might be challenged by the theological implications of life beyond Earth. In either case, the dialogue between science and spirituality would deepen, potentially fostering more inclusive and curious global conversations. From a societal perspective, awareness of life elsewhere might even influence how we treat our own planet. Understanding that life, no matter how basic, is rare, precious, and delicate could intensify efforts to protect biodiversity, address climate change, and manage Earth's resources more responsibly. If life can arise on a distant world under harsh conditions, it reinforces the miracle of life here and the responsibility we hold as its stewards. And finally, for the everyday person, for the child looking through a telescope, the student reading about exoplanets, the dreamer staring at the stars, it means hope. Hope that the universe is not cold and empty, but alive and filled with stories yet untold. Planets like K2-18b may be far away, but they bring us closer to understanding our place in the grand cosmic web. In the end, the story of K2-18b isn't just about one planet or a few chemical signatures. It's about us, our reach, our curiosity, and our eternal quest to find meaning beyond the stars.